In this video, as you can see, the objective is that students will be able to identify local extrema using the first derivative test. If you're in my class, we have already talked a little bit about local extrema, and we have definitely talked about absolute extrema and using the extreme value theorem to find the highest y value and the lowest y value on a function that is continuous on a closed interval. Here we're going to focus just on the local extrema, local maximum and local minimum. So if you take a look at the graph that you see on the screen, we have a graph whose name is f, and clearly there are some local extrema, local max, local min, on the graph. So let's begin by just walking through, and if you're in my class, you might want to complete this yourself and then just come back and see if you agree with the answers that I got. So number one says we're going to look at the given graph and identify any increasing intervals. So clearly we're looking for anywhere that the graph goes upward or increases. So the graph is going to increase. We start with a closed interval on A because that is an endpoint. The graph increases from A to B. That's an open interval at B. Then the graph increases again, beginning at an x value of c with an open interval to d on the open interval. And then again, the graph increases beginning at an x value of e all the way until we get to the other endpoint of h, and I'm going to put a closed interval on there. So the function, the original function, is increasing on these intervals. 1a asks, what is true of the derivative on all of the increasing intervals? Well, if you look at the first interval, I'm going to color in green to the best of my ability, like that. So in these increasing intervals, you'll notice that the slope of the tangent lines in those regions is always positive. Therefore, we can say that the derivative on these intervals, f prime of x, is greater than 0, or you could write is positive. All right, let's go on to look at number 2. We're looking for any decreasing intervals. And again, these questions are pretty basic in terms of identifying increasing and decreasing intervals. We can do that with some Algebra 2 knowledge or even Algebra 1 knowledge. We see that the function, original function f, is decreasing on this first interval. Sorry for my not coloring very well. I'm using a new tool here. So we have two decreasing intervals. The first decreasing interval begins at B on an open and decreases until we get to an x value of c. And then the original function decreases again, beginning at an open interval of D, and decreases until we get to E on the open interval. And similarly, we can see that the slopes of the tangent lines in those regions would be negative. So what's true of the derivative on all decreasing intervals? We will say specifically and precisely the first derivative of x is less than 0 when the function is decreasing. These are, again, ideas we've discussed in class, but we're just kind of formalizing them now. All right, let me move this up. Next question, problem or question number 3, identify any turning points. Well, we can see that the original function has a turning point at x equal to b. We have a turning point at x equal to c. Another turning point at x equal to d. And our final turning point on this interval is x equal to e. 3a, what's true of the derivative at all of these turning points? Well, if you look up at the graph, you can see that at b, c, and e, the first derivative is 0. So we'll say the first derivative is either 0, or you'll notice when you look at d, the first derivative is undefined. And that should be reminding you of a definition that we have talked about in our class. That indicates that not only are these guys turning points, but they are also critical numbers. As you recall, a critical number is any value of x where the first derivative is either 0 or undefined. And take a look at what you see in number 4, which asks you to identify any critical numbers. So I'm going to draw an arrow to say all of the numbers in 3 would go straight down to number 4. And the next question asks us, let me move that up a little bit, what's true of the derivative at all of these critical values, or critical numbers, I'm sorry. And we see the same thing, that the first derivative is either 0 or the first derivative is undefined. So, again, things that if you're in my class, you've already experienced these things before. We're just kind of the next part. Number 5, in general. So let's make some conclusions about what we've noticed about an original function versus the first derivative. So what we're really looking for here is, what does a first derivative function or graph tell us about the original functions? So it's unveiling the mysteries, and that's why our packet's called Mysteries of the First, or Mysteries of the First and Second Derivatives. So if the first derivative, and I'm reading letter A here, if the first derivative is positive, what can we conclude about f of x? Well, f of x is increasing. And we saw that from from the other side, or just by continuing to look at the same graph. Letter B, if the first derivative is negative, what did we know about the original function? Well, if the first derivative is negative on a particular interval or at a particular value of x, the original function is decreasing. And letter C, if f prime of x, or the first derivative, is 0, we know that we have a, well, you know what, let me edit that, because I need to add something in there. Hopefully you've already figured out that I should have said something else. If the first derivative is 0, and let's see if I can squeeze that in there, or undefined, then what do we know about the original function? We know that there are critical numbers at those particular values of x, at each x. Okay? Formalizing things we already know again. Now, here's where we're getting down to where we're going to do some justifications regarding local maximum and local minimum. If the first derivative changes from positive to negative, all right, so let's go back up at our graph and see where the first derivative changes from positive to negative, and one place would be at b. So the first derivative in that first region is positive, and the first derivative in the next region from b to c is negative. So if the first derivative changes from positive to negative at a critical number, so we have to establish that, then what do we know is happening at x equal to b? Then there is a local or relative max at that value of x. Very important. This is how we're going to justify our local extrema when you see an example in a few minutes. All right, moving that up. Likewise, if the first derivative changes from negative to positive at a critical number, then there is a local, sorry about that, my handwriting, I'm working on a new device here. There is a local minimum at that critical number. Okay, make sure you really internalize that, and if you go back and look at the graph at the top, you can see that the graph supports what we just talked about. All right, then number 6, sketch the graph of a function where the first derivative is 0, meaning that we have located a critical number because the first derivative is 0. Okay, so there's a critical number at c, but we want neither a relative maximum nor a relative minimum. We've actually talked about this in class. If you think about the function of x cubed, which flattens out at x equal to 0, in this case, on this graph, at x equal to 0, f prime, the first derivative of x is equal to 0. Oops, yes. Which indicates a critical number, but notice f prime of x, the first derivative, the slopes, do not change sign. So if you look up at the graph, notice that as we're moving towards a y value of, an x value of 0, the graph, the function itself, the original function is increasing, so all of the slopes are positive. And then if you go to the other side of 0, the function continues to increase, and all of the slopes are positive. So since there is no change in sign, even though we have a critical number, we have neither a local max nor a local min. So how are we going to apply this to a problem-solving situation? So let's take a look at number 7. And the way that I do this problem is exactly how my students, I expect my students to write, to show, and to do their work on a problem like this. Number 7, find the open intervals on which f increases. So we're looking for where the original function increases and decreases, and then we want to identify any relative or local extrema. So as we already know from previous work that we've done in class, the first thing we need to do is to find the first derivative. And the first derivative here is 3x squared minus 3x, using the power rule for each term. And then we're going to set the first derivative equal to 0 to get critical numbers. And I'm going to factor a 3 out of that binomial. And my critical numbers are x equal to 0 and x equal to 1. Now, the next part we have not done yet. We've done informally, but not really formally. Those critical numbers, and I did not write that, but we have two critical numbers. And as we've learned in our earlier notes, those two values of x are possible candidates for local min or local maximum. Now, keep in mind, we're not doing the extreme value theorem. We're not looking for the absolute max nor the absolute min. In fact, we don't even have a closed interval, so we couldn't even do that at all. So to determine what's going on, you are required, at least in my class, to create a first derivative number line. It is very important that you put the name of that number line on the number line. So I want to see that f prime of x that you see on my number line. All right, take your critical numbers and put them on the number line. So I'm going to put 0 and 1. Now, those two critical numbers divide my number line into 3 regions: to the left of 0, between 0 and 1, and to the right of 1. What we're going to do is we're going to use the first derivative. That's why we've named it. We're going to use the first derivative to determine when and where the original function f is increasing. How we're going to do that? We're going to choose one number in each region, and we're going to substitute into the first derivative to determine the sign, the outcome. So, for example, in region number 1, to the left of 0, I'm going to use, and you don't have to write these when you're testing, I'm just showing you what I'm using. I'm going to use -1 to determine whether in that region the first derivative is positive or negative. The way that I'm going to do that is I'm going to substitute -1 into my factored form of the first derivative, because it's a lot easier to use. Keeping in mind, I only need the signs. I do not need the actual value that I get when I substitute in -1. So when I substitute -1 into the first factor of 3x, I will get a negative. And when I substitute -1 into the second factor, I will get a negative. And a negative times a negative is a positive, which tells me, and again, in my class, you must show me that the original function, I did that in red, the original function increases, because we're using the first derivative information to tell us about the original function. All right, now I'm going to choose a number between 0 and 1, like 1/2, and I'm going to do the same thing. I'm going to substitute into the first factor, and I'll get a positive. Substitute 1/2 into the second factor, and I'll get a negative. A positive times a negative is a negative, which tells me that in that region, the original function is decreasing. The arrows are required. In the third region, I'm going to choose the number 2, and I'm going to substitute again into the first factor, which will give me a positive. The second factor will give me a positive, and a positive times a positive is a positive. Therefore, I know that the original function is increasing on that particular interval. So what you see in red is the behavior of the original function, which is what we were trying to find out about. So then I would say, because the first question was, where does f increase and decrease? This is how I want you to write your answer using precise language and mathematics. F of x increases on the interval. We're going to start, the first interval is from negative infinity all the way up to 0. I'm just reading my number line. And then again from 1 to infinity. And then we have to justify, because f prime of x, the first derivative, is greater than 0. You could say f prime of x is positive. Likewise, I'm going to now identify my decreasing interval. I have one decreasing interval, and I'm going to start by talking about the original function, f of x decreases on the interval from 0 to 1 because the first derivative is less than 0 or negative on that interval. So we're always using the first derivative to support our reasoning about increasing and decreasing and local max and local min on the original function. All right, I'm going to erase that so I can now go back and write up my local extrema. If you look back up at the graph, you can clearly see by following the red arrows that there is a, and I'm going to put a, let's see, a green dot to do that. There's a local maximum up at the top and a local minimum down here at the bottom. So we can see that using the arrows that we did for the original function. So I'm going to write up my local maximum. This is exactly how you write it up. A local, or you could say f has, a local max occurs at x equal to 0 and is f of 0. In other words, I'm saying this is how you would find the y value. So I've stated the x value and I've stated the implied y value, and that's all you have to do. You don't have to actually calculate it. A local maximum occurs at x equal to 0 and is f of 0 because, make sure you really get this, start by telling me or the reader that there is a critical number at 0. How do you do that? Tell me what's going on. The first derivative is 0 at 0, and the first derivative, don't put a 0 there, the first derivative itself changes from, and just read your graph, positive to negative. So all I'm doing is looking at that graph and telling a story. You have to write all of that as your justification. And then likewise, you might want to stop the video and write up your local minimum to see if you can do that. I'm going to erase what I wrote here, and I'm going to write my sentence for what I would say for the local minimum. So I would say a local minimum, you could say relative, occurs at x equal to, reading the number line, 1, and is f of 1, there's your y value, because now support yourself with the first derivative, f prime of, whoops, let's back that up. And again, I'm sorry that some of this is a little bit hard to read. I'm getting used to new technology. Because f prime, the first derivative at 1 equals 0, that establishes a critical number, and the first derivative itself changes from negative to positive. You're just reporting what anyone can see on that number line, but you have to file the report. All right, I'm going to